Hello and welcome. So this is a session of mechanics of materials. So here I am going to take about stress and strain diagram for mild steel. So here we are going to talk about mild steel, how it's behave when we are going to testing for stress and strain diagram. So to test this material, generally we use ultra UTM universal testing machine, and here that a specimen we can generally take, that is a circular cross section and a rectangular or a square cross section specimen we take. So here when we are testing with UTM, so what happens, we are going to clamp both the end with the UTM and going to apply a pull force from both the end, that is tensile force, which is applied on the material, that is a mild steel material. So how it's going to behave? So if we see the stress strain diagram, here a strain is taken at x-axis and a stress is taken at y-axis. So while we are applying the load, how stress and strain is going to vary? Here point A, which is called a limit of proportionality, and at this point, when due to application of load the material attains this point, means a stress at proportionality limit. After removal of load, uh, a specimen is or material is able to regain its original shape and size. So this is a benefit. So this is called as limit of proportionality, means from this point there is a 100% recovery in the shape and size after removal of load. But if we go to point B, this point B is called elastic limit. So this point B is called elastic limit, means up to point B there is a probability or chance to regain its original shape, but at point A there is a 100% recovery is possible, but from point B it may not be 100%, but recovery will happen. So from point A yielding will start, material will start yielding from point A. So it goes to point B, from point B also there is a chance of recovery. So that point B is called elastic limit. Okay, elastic limit means it will recover, material shape and size will recover after removal of load. So here a stress, point A stress will be a stress at proportionality limit. Then point B, this will be elastic limit. Then it goes to point C. Here point C is called as upper yield point. When we say it is upper yield point, then what will happen? Material started yielding from point A to B, elastic limit, then upper yield point. After upper yield points, it's going to come down. That whatever yielding happens here, maximum yielding happens in this zone, but at the point D that yielding will be less. So from point A to D we call as yielding zone, and point C is called upper yield point, and point D is called lower yield point. If we take a zone from point A to D, this is called yielding zone. Further, if we increase the loading condition or loads, further that material going to elongate, and it will be under hardening zone, strain hardening zone. Means material will sustain, is not going to fail up to point D. This zone is called strain hardening zone. Okay, after strain hardening zone, what happening, this material start yielding and it will reach to failure point. Ultimately at this point, at point F, the material will fail, it will break. So breaking will happen. So as we consider point C, so here corresponding to point C we will get yield stress. Corresponding to point E, so here we have ultimate stress, means maximum stress will get at point E, that is called ultimate stress. That is corresponding to E we have sigma U, ultimate stress. But this is not real, as we, so from this point, if in reality we will see, this will goes up and it will attain true failure stress. That is, in corresponding stress we have written sigma F dash. This is a true failure stress, means this will be tangential to this line, and it goes to point, you can say A, B, C, D, E, F, you can say G. Okay, so it will reach here. So as we see in x-axis we have linear range. Linear range means it's 100% recovery is possible. Then yielding zone, A to D material will yield, means it will lose its capacity and it will deform. So there may be a permanent deformation, and then it will go to strain hardening zone, that D to E. Again necking zone, necking will start from point E and at point F is going to fail. So here as it is written as elastic zone, that is from point O to B. So here O is taken, so point O we can write is origin. O is, can say it is origin. So here elastic zone up to B, means material shape is recoverable after removal of load. But beyond that we can say it is a plastic zone. In this plastic zone there may be yielding, strain hardening and necking. So here D is the strain hardening, sigma Y yield stress, sigma U ultimate stress, F is the failure point. Next, what happens when load is increasing through UTM? There may be necking zone, that material at a place will displace due to increase in temperature. That particle under this material will be under movement, and this will be, that particle will be dislocated from one place to another place, means going to have shifting from one place to another place. And due to shifting of materials is going to form a neck zone. So this will form a necking zone. After necking zone, next stage is going to fail. After failing, it's going to maintain a shape that is called as cup and cone shape. So one side, after breaking, one side it will become like cone and another side will become like cup. So this phenomena will happen when we test a mild steel material through the universal testing machine. So this is a concept of stress strain diagram of mild steel. So thank you so much.